So the Dalton model of the atom is childish in terms of how simple it is. It just says that atoms are composed of these spheres of matter that are indivisible. We call them atoms, which literally I think comes from the Greek to mean indivisible. We nickname this the billiard ball model because Dalton is suggesting that atoms are like billiard balls. Okay, it's something that we're familiar with in the real world, and we can say, oh, okay, that's what he's saying an atom is like. But it didn't take into account the presence of electrons, which were discovered by J.J. Thomson. So J.J. Thomson incorporated the concept of electrons into Dalton's model of the atom. And it doesn't really matter why, but he had reasons as to why it wasn't this solid sphere with negative electrons embedded within it. It has to do basically with the fact that Thomson knew you could remove electrons from atoms, and he had reasons to believe that the electrons were not just hovering around on the outside, they were distributed throughout it. So he came up with this model. However, yesterday we looked at Thomson's model kind of literally having holes poked in it by Rutherford, that the alpha particle scattering that Rutherford and his assistants observed could not be explained if you assumed that Dalton was right or you assumed that Thomson was right. If Dalton was right, virtually every single alpha particle should bounce back based on the density of atoms in gold. And if Thomson was right, based on the distribution of charge in Thomson's atom, there should never be a concentrated amount of charge which would deflect any alpha particles, so they should go right through. So he came up with this, and this I pulled from your textbook. I think this is cheap. I mean, I know it's not university physics, but for a high school physics textbook to suggest that that's what Rutherford is claiming an atom looks like is ridiculous. It's insulting, I think, on some level. That's a better one. That's just something that I constructed, and I'm not, claiming that other textbooks don't have that, but this high school textbook, for some reason, just has some weird picture. The electrons are very, very tiny. They're tinier than what I've drawn. I've drawn them that big so you can see them. The thing that this diagram is lacking is the electrons are not just in a plane orbit, not a flat orbit. They're orbiting in lots of different directions. There's a positive nucleus, and you need to understand that based on the high amount of charge and the concentrated amount of mass in the nucleus, that's what explains the scattering of the alpha particles. It explains why very few bounce backwards, because it's a hard target to hit, isn't it? It's a tiny target. But it explains why every other alpha particle is deflected, because if an alpha particle goes close to a nucleus, then it will be pushed away from the nucleus. If it goes closer, it will be pushed further away. And if it happens to go through the atom at a reasonably far distance from the nucleus, it just it just moves a little bit out of its path. But yesterday we said that this atom violates Maxwell's principles of electromagnetism. In a nutshell, Rutherford is claiming these electrons are in a circular orbit, which means they're accelerating. But Maxwell said correctly that any accelerating charge will generate electromagnetic radiation, which is a form of energy. And Bohr is the fellow who's going to come up with the way around that. And when you hear what Bohr's solution is, it's not very satisfying intellectually. Okay? But the Bohr model of the atom removes this violation. The other thing, and this is what we're going to focus on today, is this model of the atom cannot explain line spectra. So yesterday we looked at some line spectra, bright line spectra, through a diffraction grating. You know what I'm talking about, right? Okay. So even something as simple as hydrogen that has 4 specific wavelengths, one of which there's no way you could see in this lab. There's too much ambient light. But even something as simple as hydrogen produces 4 specific wavelengths, and a hydrogen atom has a single proton and a single electron, so somehow they're in cahoots with each other to produce those wavelengths. And a good model of the atom would explain what's going on. That led us to types of spectra. We'll have lots of opportunity to review this before the end of the unit, but continuous spectra are produced by hot glowing solids. Bright line spectra, which we sometimes call emission spectra, Spectra is plural of spectrum. Emission spectrum are produced by excited gases, hot gases, and dark line spectra or absorption are produced when white light from a black body goes through a cool gas. The cool gas absorbs certain wavelengths. This is what they look like. This happens to be a depiction, this middle one, a depiction of the hydrogen bright line spectrum, the one we looked at yesterday. But again, I'll show you what it actually looks like up here as best I can in a second. The likelihood of you seeing that violet line is pretty slim. Okay. And the dark line spectrum for hydrogen is the same. So where we kind of left off yesterday, as I said, whatever's going on, there are certain wavelengths or energies that hydrogen is allowed to accept, and it's the same energies or wavelengths that hydrogen is allowed to kick out. So whatever can go in can come out. Spectrometer is a device used to separate wavelengths of light into its colors. So this, I'm showing you the best I can give you for that pinkish light that we saw for the hydrogen spectrum. And if I just take a screen and cut a tiny opening through it, and you were on this side of the screen looking, you wouldn't see that whole thing. You would just see a line of light. That's what we're talking about. And if I put a diffraction grating there to spread out the light, this is what happens. This is the n=1 images. What was happening yesterday, by the way, is, Christian, you were doing it, right? Okay. We were not shining the light through a diffraction grating on a screen. The screen was Christian's eyeball. He was standing over here looking towards the light. But what happened was he would have seen the red light in this direction, and he would have seen the green light in those other directions. So the angles that we were measuring are the same as the angles that we would see if we could project it on a screen. There's just not that much light to do that. It's always you're looking into the light rather than projecting the light onto something. So these are the 4 wavelengths of hydrogen. And again, the combined light is pink, and you couldn't, I don't think anybody would claim you could see the violet one, could you? I would suggest maybe if you thought you could, you weren't. You were maybe either hallucinating or it is an optical illusion. It's just too dim. What I asked you to do yesterday is to use the data to find the wavelengths, and we'll come back to that in a bit. But the point is, I can analyze light from a hot gas and measure the wavelengths through this experiment and identify what the gas is. Every single element or atom has its own unique spectral signature or thumbprint. And molecules do as well. If you heat up water vapor, it has its own spectral footprint or fingerprint. And it's not just oxygen and hydrogen combined, it's different. If you use, and I put this here because you never know when you might encounter this, and I think you're a curious lot. So if you use a prism spectrometer, this is what you do. Now, how is it you go about finding the wavelengths? Prism spectrometers are very, very accurate. But there's no formula to relate how much the light refracts to its wavelength, unlike interference. What you would do is you would use Snell's law to find the index of refraction of that color in the glass. Remember that every wavelength has a different index of refraction. Once you know the index of refraction for the red and the green and the blue and the violet, you look at data. You look at a graph and you locate the index of refraction on a graph and you identify the wavelength that it must be. There are 3 graphs here, just so you know. The x's are measured values, so those are empirical. The other 2 are different formulas that can be used to predict them. But within the visible region, everything is matching. So, continuous spectrum. What are we looking at? Solid glowing object goes through a diffraction grating, you get continuous spectra. Bright line spectrum, and those are the wavelengths for hydrogen. How many of you calculated the wavelengths? Little disappointing at first. We'll talk about them in detail in a bit, but it's not bad considering how I was measuring L. Remember, for me measuring L, and I couldn't see in the dark anyway, who knows if what I actually read was the true measurement. I took the meter stick, I put it against the diffraction grating, and I put my hand here, and then I slid this over, and I measured the rest of the distance. It's still not bad because I think the biggest percent error is 9%. And what we've said is in high school physics, within 10% is acceptable. If you were to do this by putting that spectral discharge tube on the back counter and taking your diffraction grating and putting it against the countertop and looking through it and measuring accurately your L and your X, I guarantee you, you'd be within about 2%. But we just didn't have time to set that up. This is what a dark line spectrum looks like. And again, it's hydrogen, so this gas here would be hydrogen. So the difference here is that a bright line spectrum starts off with hot gas. The dark line spectrum is produced by taking a continuous spectrum and allowing a cool gas to do its thing to it, to remove wavelengths.